In the previous video, I made a stable magnetic base for a dial indicator. If you haven't seen that video yet, you might want to watch it first. In this video, I build the adjustable arms of the stand, using a human arm as an example. The shoulder, elbow, forearm and wrist are designed, calculated and made in this video. I hope you enjoy watching it and find inspiration in it. This is the design for the shoulder joint. I'm going to make it from silver steel so that I can harden it later for extra strength and wear resistance. A threaded bolt extends through the two clamping blocks so that the block wings can be pulled together. I will later regret that this bolt fits into the blocks without any play. My tiny tabletop bandsaw comes in so handy here. The machine has no trouble with this 40mm thick steel bar and neatly cuts smooth and straight slices and blocks. If you want to know more about this machine, watch the series about its construction on this channel. And the parts for the shoulder, except for the large knob that I make off camera, are now ready. Let's first test whether this design is sufficiently rigid and allows smooth shoulder movement. This is the commercially available magnet standard. The deflection under the weight of 1/4 kilo is 400 micrometers. And the deflection in my construction turns out to be 134 micrometers. A lot less, but I am anything but satisfied with this. The knob needs to be tightened much tighter than I expected with such a fine thread, and the flexibility of the shoulder joint is too great. Some thinking led me to realize that I had made a design error. The bolt fits through both clamps without any play, which means that the deformation in the clamps that will always occur when tightening will cause these clamps to become stuck around that bolt. I don't want to solve it simply by reducing the diameter of the bolt, because then I introduce unwanted play. I'm going to make a better shoulder joint. This is much better. Not only has the deflection been reduced to 96 microns, a slight tightening of the knob is sufficient to properly lock the shoulder joint. Of course, I also did some calculations here, and that led to an estimate of the flexibility of that joint. At just over 10 microns, this is much better than the 127 microns in the commercial model. For the design of the elbow, I used the commonly used ball head. By tightening a bolt, 2 clamping wedges are pressed very tightly against the hardened head, which in turn becomes clamped in a ring. On my to-do list, design and make a decent radius cutter tool. This is just junk. If you want to know more about this small grinding machine, see the series A Tiny Tool Grinder. To enable smooth fine-tuning, I first build a forearm. To maintain the biological analogy, I call the parts of the arm the radius and ulna. The two are pushed apart by a fine pitch screw. If both parts had the same cross-section, they would both deviate from each other by the same amount. By making one part slightly thicker than the other part, and allowing only this thick part to connect the elbow and wrist, I get the desired weakening of the displacement by about a factor of 10. For the wrist, I use the same principle as for the elbow, a ball head with a clamping device. All parts are finished. Most of it is made of silver steel and can soon be hardened and tempered, but some parts are made of mild steel. I will carburize, also known as case hardening, these parts in my electric oven. I just use aquarium carbon and sodium carbonate, which works well, clean and easy. If you would like to know more about this and the hardness tester I built, view this series How Hard Can It Be? Here, under the microscope, the small pit that the tester's diamond has pressed into the material is visible. The length of the diagonal is a measure of hardness. I let the steel absorb carbon at a temperature of 880 degrees Celsius for 2 hours. This should lead to an outer shell, a case, of just over half a millimeter thick. That should be sufficient for a stronger and more wear-resistant surface. The steel has become very hard after quenching. Too hard, because now also brittle. Tempering is the answer to that. After tempering the steel at 220 degrees for 2 hours, just on my electrical stove, the hardness has decreased somewhat to about 55 Rockwell C. Now the brittleness is gone, but the hardness is still there. After thoroughly cleaning the steel parts, I give them a cold bluing treatment and allow a layer of oil to penetrate the black surface. All parts are ready. Time for the best work, the assembly, and of course the final test. The differences with the commercial model are significant. There is much more stability and adjustment is quite smooth, especially for such a slim adjustable magnet stand. If I compare that with all that annoying fiddling with that much too rough adjustment of an unstable arm in order to set it to 0, the progress is very good. I do have some wishes when it comes to the design. The whole device works fine, but the arm could look more attractive and streamlined. Maybe something for the near future. One final note. The drawings you see in this video are nothing more than rough sketches. They will provide plenty of starting points for a build, but you will definitely have to use your own brain and understand the necessary small nuances. So they are certainly not suitable for blind replicating. See you next time.